Well, thank you for the very thorough introduction, Maria. It's much appreciated. Saves me a little bit of time. So just as a little background, Dr. Lee visited Penn State and did this investigation, fortunately for me, because this was a project that started quite some time ago. I'm going to say in the early 2000s with funding from National Science Foundation. And some of you in the US know it's probably impossible to get follow-on funding to actually finish long-term experiments. So Jaeha was kind enough to come and do this and write this paper. And it's my honor to present this work today. So so the topic is on some long-term conditioning of beam specimens. And as I'm not going to give like a detailed literature review on this or anything. I'm sure a lot of you have seen this. If you're in this session, you're interested in this subject. But there's a lot of effects of different things on bond between externally bonded FRP reinforcement and concrete. You know, among them, you have freeze-thaw going on due to weathering outside. You have water outside. You have ultraviolet exposure outside. Temperature variations, and we've heard a lot about these things over the years. But a long time ago, when we first designed this project, what we were thinking about at that time was, what about a natural outdoor environmental exposure? And what about in combination with sustained loading? At that time, anyway, there was practically no work done on applying a sustained load and then throwing on top of that the natural variations in climate conditions that go on outside. So that's what we decided to do, and the objective here today is to talk about the results of some long-term testing where we have kept beams under load for a total of 13 years and finally took them off. And we have some intermediate data at 6 years. Of course, we got zero time data and did some bond tests following a sustained loading period. And that picture there shows just a picture of these beams. I'll talk in more detail about how we designed this experimental program and then go over the results from the fracture behavior, basically getting the Mode II interfacial fracture energy from that kind of a specimen, a beam bending kind of a specimen. So first a little bit about selection of a specimen. And, again, keep in mind this was done 20 years ago. And there was really not much around in the way of standardized test methods. Most people at that time were using one of those two kinds of specimens that are on the top here. And we decided that this was not that convenient to use for sustained loading in a robust way for a lot of years. Sitting outside behind a chain link fence behind a research building or something like that. So we decided not to go with those because we thought they were a little too fragile for that kind of exposure condition outside. And so what we ended up doing was going with, like the photograph on the previous page, a double beam setup, restrained at the ends, springs in the middle that provide a 4-point loading situation maintained over a bunch of years. And the springs in this case were compressed considerably, about an inch or so, for those of you who think that way in inches. And so the variation in the load due to creep or something like that is fairly small because if you get a little bit of deflection out of 1 inch, that's, actually a pretty small percentage. We looked at that as to how much the spring compression height changes. It's actually pretty small, within a few percent, I would say. And we were actually adjusting it within the first year to maintain a constant spring compression, but found out it really wasn't necessary after that. This is a lot of stuff to look at, but first just some basic background. This is on GFRP. We did CFRP also. For this paper, I didn't include that, so we're just talking about GFRP because for one reason or another, we had a lot more data in the case of GFRP versus CFRP. The little information on the concrete there, we had two different mixes that provided roughly 21 and 41 MPa strengths. We had coarse and fine aggregates in the concrete. We did not put in any air entrainment admixture. I get that question often, and so that's something to keep in mind. The epoxy itself is a 3-part system where you have a primer and then you have a putty to level out the roughness and saturant. Properties are there. You could look at them in the paper if you'd like. I'm not going to spend time on that. A little more detail on the design of the specimens. They're about 1 meter long, as you can see there, and 100 by 100 millimeter in cross-section. They are designed to fail by debonding. We initially use a saw to cut a starter notch, as we call it, and then we fill that notch with foam. And after that, we grind off the top, clean it up, and then go ahead and apply the FRP system on top of that. The crack after we were done, after the FRP has cured, we put that beam into a load frame in 3-point loading, and we load it up until the concrete cracks and develops a crack which goes a good part of the way through the cross-section. Remember, there's no steel in this beam, so when you crack them, that crack goes, probably 80–90% of the way through the cross-section, so they're pretty fragile in handling them after the pre-crack stage. So once they've been pre-cracked, then they're ready to go into the sustained loading rigs, as you can see here with the springs. We already talked about that. The sustained loading value was selected to provide about 13% of the guaranteed rupture strain in the FRP, which turns out to be about 2,700 microstrain. And so again, the idea is to maintain that over the course of years by use of those springs. And a couple of pictures on the bottom there showing the inside the lab, outside in the wintertime, and outside in the summertime. So what about that natural conditioning? We're located in Pennsylvania. Those of you not familiar with Pennsylvania State University, we're in the middle of Pennsylvania, there where that red star is. It's called a warm, humid continental climate, although at this time of the year you wouldn't know it was warm. The temperature, as you can see, fluctuates between maybe +30 and -20 over the years. And if you count the freeze-thaw cycles, according to the climate agencies, they say 65. Not sure exactly how that's calculated. It might not be within the FRP itself, or within the concrete, but that's what they're calling the climate people say 65 per year, which is 840 over 13 years. All right, so after the conditioning, we get rid of the springs, we take the specimens back into the lab, and we do a 3-point loading test. So the idea is to debond the FRP from that starter crack, and then it grows outward in 2 directions from that. We do strain monitoring so that we could characterize strain distribution, and from that get the fracture behavior of the material. We used 2 methods early on. When we did the 0 time back in close to the year 2000, we did not have the availability of digital image correlation then, so we were using photoelastic strips. I don't even know if anybody uses photoelasticity anymore, but it's an optical technique where you put a piece of reflective plastic on top of the FRP. You look at it with polarized light, and then you translate the colors into strains. It's a lot easier now with digital image correlation. As you can see here, all that stuff is done pretty much automatically by the computer. So that was done at year 6, digital image correlation, and also at year 13. We also put 3 strain gauges in the vicinity of the notch, right at the notch, and plus and minus 1 inch away from the notch. After the test, as I said, the specimens were designed to debond, and we were able to rip off the FRP from the remaining part of the concrete and then core out some small cylinders and then do compression tests on those cylinders to measure the strength of the concrete to see, so that we could account for how much the strength increases over time. Failure mode looks something like this. You typically get debonding for some distance, and there's secondary cracking going on, sort of like tooth cracking near that pre-notch. And then for one reason or another, very often the FRP would fracture at some point after delamination had grown a bit from the starter crack. In this paper, we're not going to be talking, I've presented this stuff elsewhere about the fracture strains, but we're going to focus here just on that initial part of the debond growth. So the procedure goes something like this for analyzing the strains. We acquire the strain data by whatever technique we're using, photoelasticity. This example is for digital image correlation. These little orange dots are the strain gauge data near the notch. And as you'd expect, they match up pretty well. And we let the crack grow. Usually it jumps in increments, and at each of those stages we record more data and are able to characterize the fracture energy as the crack grows away from the crack. Next step is basically a backtrack, if you will, because we found a lot of trouble trying to fit our strain versus position law, which, by the way, we're using this paper down here in the bottom for the strain distribution and local bond distribution and those kind of things. We couldn't very easily use the top left figure because there's a lot of variation in the very local strains. So we basically integrated it to get slip versus position and then fit that form of the theoretical equation from that paper. Third step is to go back to strains again, and now you can see it fits fairly well, and so you don't have to deal so tediously with all of that noise in the data. And then finally, again, using that equations developed in that paper by Zhu et al., we can find the local bond stress versus slip behavior. All right, so getting into the results, the concrete cylinder testing, strength went up over time as you'd expect. This is outdoor for the stronger strength concrete. You can see that at 6 years, it went up, and then at 13 years, it went up a total of 33% over those 13 years. The indoor didn't go up quite as much, 22%. The red lines down here are for the lower strength concrete, and that went up even more outside, 46%, and then indoors it went up by 8%. We use this information to account for the increase in the strength of the concrete by using this equation by Liu and that gang over in Hong Kong, which has the strength of the concrete involved. We do a transformation of the cylinder strength over to the tensile strength, which goes into this equation, plug in our geometry of the FRP and the beam, and that actually can make a prediction of the fracture energy. Now, it won't agree exactly, as you'll see on the next page. So this is some sample data. This was taken from the outdoor specimens after 13 years. The black ones are at 0 time. One thing you'll notice about the 0 time is that they're all above the prediction by that equation. And that is maybe not too surprising. People who've done beam experiments tend to see that kind of thing, whereas that equation is more developed for pull-off type testing as opposed to beam type testing. The other thing about the 13 years is you see a lot of variation there and you see a lot of points. We actually didn't have that many beams. But what we did, as I said before, is we characterized the GF, the fracture energy, as the crack grew away from the pre-notch. So there's actually a lot of different measurements from some single specimens that are embedded in there. So a lot of things cause up and down depending where you're measuring GF as the crack grows away from the starter notch. This is just 4 more sets of data. I know this is a lot to look at, but it's basically the same thing I just showed you, but for all these different conditions of indoor and outdoor, 6 years and 13 years. And it's basically the same conclusion, which is that the data after years of conditioning is up and down depending where we measure the fracture energy, and of course depending on the environment as well. We're interested in the environment. Okay, that's what we want to do. And so we're going to use this equation up above here to take care of the variation in strength over time so that what's left is the effect of the environment. How do we do that? Well, here's an example. These are 2 different specimens here. This one was outdoor at 5. That's a mistake. That should be 6 years, sorry. And you can see as this axis here in the bottom is distance from the pre-crack, vertical axis is fracture energy, and you can see that as the crack grows, the delamination grows away from the crack, the GF goes up. Okay, now there could be several reasons for that. One that has been talked about a lot is the friction between the FRP and the concrete. So that happens in the beam test. Another possibility is that the part that is subjected to the sustained stress is only near the notch. And as you grow the delamination out of that region, it's possible that there could be a change in GF as well as you get into the part of the FRP that was not seeing the sustained stress. The typical zone of bond transfer, if you want to call it that, is somewhere in, I'd say, maybe the 70 mm range during the sustained loading period. This is just another specimen that shows kind of the same thing, so I won't go into that. So what we're going to do is use that variation in the GF that's expected due to the variation in the strength of the concrete over time to factor out or normalize, if you will, the fracture energy normalized by the strength of the concrete. So how do we do that? That's done by this equation here, basically taking our measured GF and dividing by that equation that I showed you earlier, which accounts for GF due to the strength of the concrete. And then hopefully what's left is the part due to the environment. So let me go through this pretty quickly. I'm going to summarize it on the next page, so it'll be a lot easier to interpret. But let me first say something quick about ultraviolet. We didn't have a lot of ultraviolet data, but these hashed bars are the ones that were facing upward in those pairs of beams, so they would presumably see more ultraviolet. And the solid ones here, and these outdoor, these are 13-year specimens, were facing downward into the asphalt, and so they may not have seen as much ultraviolet. There's really not a lot of difference except for this one down here, and so we don't consider that to be a very strong, and I'd say a null effect due to ultraviolet, if you consider that to be even a valid test of ultraviolet. So nothing really stood out there. Second, if you look at the 0 time versus 6 years indoors, you see plus 81% on average in the fracture energy. If you go out to 13 years, you see minus 18% from 0 time. So it went up 81, and then it ended up down at minus 18 after 13 years, and that's indoors. If you go to the outdoor set, you see plus 12 at 6 years, plus 12%, and then minus 38% at 13 years. So fracture energy went up first, and then it went down. So that can be summarized here on this page. This is the same information where we just collected the averages, and it basically repeats what I just said, that at 6 years, everything is better in terms of the fracture energy, and at 13 years, everything is worse in terms of the fracture energy. So, in conclusion, what came out of this, waiting 13 years and plus a few more years to write the papers, are the following pieces of information. Compared to the 0 time beams, 6-year beams exhibited an increase in the normalized fracture energy. Okay, after we accounted for the variation in the concrete strength, the part that's left, which would be due to the sustained loading and due to the environment, is as shown there, plus 81% indoors, plus 12% outdoors. And we think, and Maria presented a talk yesterday, which talked about the strain redistribution, which goes in vicinity of the notch when you have sustained stresses going on. And we believe that, and several other people have seen this too in the intervening years, that the stress concentration relaxes, we think, and we've seen it with the stress distributions too, which is what could be behind that improvement of fracture energy initially. Later on, though, it's a different story. As we said, outdoors minus 38%, and indoors, that's a minus 18%. Sorry, another typo there. Believed to be due to the environmental effect and perhaps the effect of that sustained loading as well outside. As I said, ultraviolet, we didn't have a tremendous amount of data there, but we didn't see any strong evidence that either direct exposure to the sunlight or indirect made any difference. And I failed to mention earlier that we didn't put any UV protection on this system. We just put it out there just the way it was. So maybe not the best procedure, but back at that time, I guess we didn't know what we were doing, so that's what we did. But nonetheless, we didn't see any tremendous UV effect. And I guess I should always put a bunch of caveats on this. Of course, you know, a lot of these things depend on the details, right, of the particular materials we used, how we prepared the specimens for what we knew back then in the early 2000s, the particular exposure conditions we had, and of course the bond test method that we used, the beam bending test method. So these things, you know, they all kind of tied up into the conclusions, I would say. If anybody's interested to see more details on this, we have published 2 papers. This is just a small snapshot of this. As I said, we have CFRP data as well. It's given in 2 journal papers. And I'll close with just acknowledging the help of the National Science Foundation and the Korea National Research Foundation for supporting Jaeha Lee's summertime work over at Penn State, and then of course a bunch of undergrad students who helped us out tremendously in this work. Thank you very much.